an efficient lamp for emergencies. Always ready to use, it does not require batteries, conventional or solar recharges, just a few turns of the crank. The realization of this lamp is the evolution of the other video I published on the electric generator for emergency situations. The work starts again from there. Only 4 supercapacitors of 24 amps 2.8 volts and the control electronics board, with 10 SMD-5050, are added. On the screen is the complete wiring diagram of this lamp, divided into 3 sections, A, B and C. The diagram of section A has already been described in the previous video. In section B, the control electronics have the precise function to limit the voltage of the ends of the 4 supercapacitors connected in series to a precise value. The LM311 dial gauge is inverting input 3 connected to the reference voltage of 4.3 volts. The non-inverting input reads the supply voltage. The voltage of the output of pin 7 will always be 0 as long as the voltage of pin 2 is lower than the 4.3 volts at pin 3. On the other hand, when the voltage of pin 2 exceeds 4.3 volts, the output at pin 7 becomes positive. The MOSFET enters conduction by discharging the voltage coming from the generator to ground, thus preventing the supercapacitor series from being charged to an excessive voltage. At the same time, the red LED will start flashing, indicating that the supercapacitors are fully charged. The potentiometer P is adjusted so that the MOSFET trips, discharging the power supply when it reaches exactly 1050 volts, the voltage of the ends of the 470 microfarad capacitor. The voltage of the ends of the series of supercapacitors powered by the 1N5406 diode will be 10 volts, so it follows that the voltage of the ends of the individual capacitors will be around 2.5 volts, a voltage of absolute safety. Considering that these 24 amp supercapacitors have a nominal voltage of 2.8 volts. As a light source, I use 2 slats of 5 SMD-5050 as shown in the diagram. These 2 slats require a voltage of 15 volts, so it was necessary to add a converter capable of increasing the voltage supplied by the 4 supercapacitors. This converter must be able to operate even when the voltage of the capacitors is very low, and must provide a constant voltage of around 15 volt. I found in the MT3608 module the ideal element for my realization. The module is capable of operating from 2 to 24 volts. The output voltage can be adjusted up to 28 volts. Its efficiency is 97%. The maximum current is 2 amperes, more than enough to power the LEDs. Now a video in which the operation of the converter that powers the LEDs is checked. On the left you can read the voltage of the input of the converter, on the right the voltage of the output. With 2 volts at the input we had 14.91 volts at the output. With 3 volts we had 15 volts at the output. With 4 volts we get 14.97. With 5 volts 14.95. With 6 volts 14.94. With 7 volts 14.93. With 8 volts 14.94. with 9 volts 14.95. And finally with 10 volts 14.94 volts at the output. I would say that the voltage is perfectly stabilized around 15 volts. This is what the lamp looks like assembled and ready for use. Now a check is made on how the potential is distributed on the 4 supercapacitors connected in series. It is reported by many that an active or passive network, via diodes or resistors, is necessary for the correct balance of the potential between the capacitors. And this is correct. On the other hand, it always leads to a loss of part of the accumulated energy. In my case, I'm going to show that my capacitors don't really need that. The lamp's supercapacitors are fully charged at 10.05 volts. The first capacitor gives me a voltage of 245 volts. The second 250. The third 250. The fourth 256. The differences are small, and considering that they withstand a voltage of 2.8 volts, we can use them safely. And now the test to evaluate the time needed for the complete charge of the 4 supercapacitors. The video has been partially sped up. After 6 minutes and 50 seconds, the supercapacitors have reached full charge. The voltage of their terminals is 10 volts. Continuing to turn the crank, we will see that the voltage does not go beyond 10.04, 10.05 volts. And at the same time the red LED begins to flash. This is the end of charge signal. Electronics intervene with the MOSFET, which discharges the voltage generated by the stepper motor to ground. Now the test on the autonomy of the lamp. Here too the video has been partially sped up. After 7 minutes, the voltage of the ends of the capacitors dropped to 823 volts. After 22 minutes, the voltage is 313 volts. After 24 minutes, the lamp goes out. The voltage of the ends of the capacitors is 225 volts. It should be remembered that the accumulated charge of supercapacitors when their voltage is below 2 volts can never be used by the system. Conclusions. A scant 7 minutes of charge allows you to have light for 24 minutes. This system is fine when using LEDs. But it's not good for charging cell phones or lithium batteries that require electrical currents in the order of amperes. In this case, it is necessary to have larger supercapacitors, and consequently also stepper motors or other more powerful generators. If you found the video interesting, subscribe and leave a like. Thank you for your attention. To the next.